You know, usually when we talk about a massive cosmic structure, there's this ingrained expectation of just incredible crushing density.
Right, yeah. Like you expect it to be heavy.
Exactly.
Yeah.
Like if we're discussing a black hole or a neutron star, the physics totally match the visual. But then you look at a picture of a giant space cloud.
One of those breathtaking James Webb images.
Yeah, exactly. And it looks incredibly thick. I mean, it looks like you could reach out in a spacesuit and just grab a handful of it. It looks almost like cotton candy.
It is entirely deceiving. I mean, we are biologically wired to trust our eyes, right?
Right.
To believe that a structure casting shadows and glowing with rich, opaque colors must have, you know, serious physical substance to it.
But when you actually step into the world of nebulae, the literal stellar nurseries of the universe, that visual intuition is just entirely wrong.
Completely wrong.
We're looking at a cosmic landscape that is fundamentally an optical illusion. What looks like an impenetrable wall of gas is actually emptier than almost anything the human brain can comprehend.
It really is.
And that is exactly what we're unpacking today. We're going on a deep dive into the sources on nebulae. And if you are listening to this right now, we are going completely down the rabbit hole to deconstruct how these vast, freezing optical illusions somehow harbor the most violent, explosive, and creative engines in the universe.
It's a pretty wild transition.
Okay, let's unpack this. It is a journey from absolute emptiness to nuclear fire, and ultimately to the literal reason you exist to hear this deep dive.
To really grasp that journey, we have to start with the raw material. At its core, according to the astrophysical data, a nebula is simply a giant cloud of gas and cosmic dust drifting through interstellar space.
Just drifting.
Yeah. And predominantly, we were talking about the primordial building blocks of the universe, roughly 70 to 75% hydrogen and 25 to 28% helium.
So it's essentially the classic starter pack of the cosmos, just hydrogen and helium, or I guess only microscopic fractional amounts of heavier elements scattered inside.
That's right, just trace amounts.
But before we get into how that incredibly sparse gas turns into a burning star, we really have to talk about how humans even figured out what these things were. Because for centuries, astronomy was just completely fooled by that optical illusion.
Oh, absolutely. The confusion is basically baked right into the name itself. Nebula is simply the Latin word for cloud or mist.
Oh, really? Just cloud?
Yeah, just cloud. And if you go back to the 18th and 19th centuries, astronomers like Charles Messier and William Herschel, they were building the first truly serious telescopes.
Right.
They would sweep the night sky, usually looking for comets, honestly, and anytime they saw something that wasn't a sharp pinprick of light, or anything that was fuzzy, blurry, or cloudy, they just threw it into a single classification bucket.
You just called it a nebula.
Exactly. They called it a nebula.
So it was essentially just a catch-all term for like smudge on the lens or fuzzy thing in the sky. They had absolutely no idea they were looking at entirely different classes of objects.
They really didn't. I mean, they had no concept of the true scale of the universe yet. To an 18th century astronomer, the Milky Way galaxy was the entire universe.
Right, they thought that was it.
So when they looked toward the constellation of Andromeda and saw a glowing elliptical smudge, they documented it as the Andromeda Nebula.
Wow.
They assumed it was just a cloud of gas sitting somewhere down the cosmic street right here in our own galaxy.
But Andromeda isn't a cloud of gas at all. It's a completely separate galaxy containing, what, 1 trillion stars?
Roughly 1 trillion, yeah. And it's 2.5 million light years away.
But because they didn't have the technology to actually resolve those individual stars, 1 trillion stars, millions of light years away, looked identical to a small puff of gas a few hundred light years away.
Exactly. It wasn't until the 1920s that the paradigm completely shattered. Edwin Hubble was using the Hooker telescope in California, which was massively more powerful than anything that came before it.
100-inch telescope, right?
Yeah, that's the one. He was studying these so-called nebulae, specifically looking at Andromeda, and he managed to identify a very specific type of star inside that fuzzy patch, a Cepheid variable.
And a Cepheid variable is basically a star that pulses in a very predictable way, right? It gets brighter and dimmer on a set schedule.
You've got it. The physics of a Cepheid variable are so incredibly consistent that the slower it pulses, the brighter the star actually is in absolute terms.
Oh, I see.
So Hubble could measure the pulse rate, calculate exactly how bright the star should be, and then compare that to how dim it actually looked through his telescope.
Ah, so it's a standard candle.
Precisely. The difference between its true brightness and its apparent brightness gave him the exact distance.
And the math must have been completely shocking to him.
It was revolutionary. The distances were impossible if these objects were inside the Milky Way. Hubble's calculations proved definitively that Andromeda and many other nebulae were entirely separate island universes.
The universe literally expanded by orders of magnitude overnight.
It did. Astronomers had to frantically go through their catalogs and reclassify everything. They were like, that's a galaxy, that's a star cluster, that's the remnant of a dead star.
That's hilarious, just crossing things out left and right.
Yeah.
Yeah.
And the word nebula was eventually reserved strictly for what it originally meant. Actual clouds of gas and dust forming stars.
Which brings us back to that density paradox we touched on at the very beginning. We have these actual clouds of gas now, and we have these spectacular images from Hubble and Webb where the clouds look like thick, opaque mountains of smoke.
Right.
But the sources tell us that in reality they are incredibly sparse. The average density of a nebula is roughly 1 atom per cubic centimeter.
One single atom occupying a space about the size of a sugar cube.
That is just, to really visualize that emptiness, we can compare it to the absolute best vacuum chambers we have here on Earth.
Which aren't even close, by the way.
Right. Even in our most advanced state-of-the-art laboratory vacuums, we're still leaving hundreds, if not thousands, of particles per cubic centimeter. A nebula is vastly emptier than the absolute best vacuum humans can physically engineer.
It really puts it into perspective.
For context, the air you are breathing right now as you listen to this has about 10 to the power of 19 molecules in that same sugar cube-sized space. That is a 1 with 19 zeros after it.
It is a near-perfect void.
So the obvious question here is, how does a near-perfect void block light? How does it look at a solid wall?
It's a great question.
I always think of it like standing in a very light, almost imperceptible fog. If you hold your hand out in front of your face, the air between your eyes and your hand looks completely clear. You can't see the fog at all.
Right, because there's not enough of it between you and your hand.
Exactly. But if you look at a skyscraper a mile down the road in that exact same fog, you can't see the building. The accumulated mist over that mile builds up into a solid gray wall.
That is the perfect way to understand it. It is entirely about the cumulative effect of matter over unfathomable distances. When we say a nebula have 1 atom per cubic centimeter, we have to factor in the sheer mind-bending scale of these structures.
They're huge.
They're not the size of a room or a planet or even a solar system. They span hundreds of light years.
And a single light year is 9.4 trillion kilometers. So if you line up 1 atom per cubic centimeter, but you stack them continuously for 100 light years, eventually those individual atoms are going to catch and block the light coming from the stars behind them.
Yes, exactly. They stack up into a physical barrier. What's fascinating here is how early astronomers were completely fooled by the lack of depth perception in space.
Yeah, space really strips that away from us.
It does. When you look at an image of the Tarantula Nebula, you are seeing a two-dimensional photograph of an object that is 1,000 light years across.
Think about that, 1,000 light years. If you were to take a gigantic cosmic spoon and scoop up a teaspoon of the gas for the Tarantula Nebula,
the actual material inside that spoon would weigh less than a speck of dust.
Unbelievable.
Yeah.
But because the cloud is 1,000 light years wide, the total mass of all that near nothingness adds up to millions of times the mass of our sun. Millions of suns worth of material constructed entirely out of a vacuum.
That paradox of scale, extremely low density but unbelievably high total mass, is the only reason they possess the gravitational weight required to eventually collapse and form stars.
But obviously, if we look at a gallery of these massive clouds, they don't all look like dark, shadowy walls. Some are glowing bright red, some are a vivid ghostly blue, and some look like delicate little soap bubbles.
Why is a huge variety?
So if they're all just massive empty vacuums of hydrogen and helium, why do they look so wildly different?
Well, those visual differences are actually a chemical and physical roadmap. They tell astronomers exactly what is happening inside the cloud, what kind of stars are interacting with it, and where the cloud is in its evolutionary life cycle.
Oh, so it's like a color-coded map.
Exactly. We can categorize them into 4 distinct physical states. The most famous, the absolute showstoppers, are the emission nebulae.
These are the ones dominating the astrophotography subreddits, right?
Yeah.
Vivid, dramatic reds, pinks, and greens.
Yeah, those are the ones. The intense colors are the result of ionization. Deep inside, or right next to these clouds, you have incredibly massive exceptionally hot young stars. Astronomers classify these as O-type and B-type stars.
Okay.
To give you a sense of scale, an O-type star can be 50 times the mass of our sun and burn at a surface temperature of 30,000 Kelvin or more. They are blistering blue giants, and they are pumping out lethal amounts of extreme ultraviolet radiation.
So that extreme UV radiation hits the sparse hydrogen gas in the cloud. It's essentially acting like a giant microwave, but on an atomic level.
It is so energetic that the ultraviolet photons actually collide with the hydrogen atoms and violently strip the electrons right off of them. That is the definition of ionization. You are left with a soup of disconnected protons and free-floating electrons. But nature doesn't like that imbalance. Eventually, those electrons are captured and recombine with the protons.
When they reconnect.
The moment an electron snaps back into orbit around a proton, the atom releases a tiny burst of energy in the form of a photon. Visible light.
The gas is literally generating its own light. It's like a colossal neon sign.
That's a great analogy.
In a neon tube, you pump electricity through neon gas to make it glow a specific color. Here, the young, hot O-type stars are the electricity, and the hydrogen cloud is the neon.
And because hydrogen has a very specific atomic structure, when that electron snaps back, it produces a very specific wavelength of red light, precisely at 656 nanometers. Astronomers call this H-alpha emission.
Ah, H-alpha. I've seen that term used a lot by amateur astronomers.
Yeah, it's very common. That is why the Orion Nebula and so many others have that rich, deep crimson color. It is the signature color of hydrogen snapping back together. If there are trace amounts of oxygen being ionized, it glows a vivid green. Sulfur produces different shades of red and blue.
But not all clouds have those massive, blistering O-type stars nearby to ionize the gas, right? What happens if the stars nearby are just average, run-of-the-mill stars that don't pump out enough UV radiation to strip electrons?
Then you get the second type, a reflection nebula. If an emission nebula is a neon sign generating its own light, a reflection nebula is a cosmic disco ball.
A disco ball, I love that.
It is simply taking the light from nearby stars and bouncing it around.
So the light just hits the dust particles in the cloud and scatters. But these reflection nebulae are almost always a very specific, ghostly blue color. Why blue?
It comes down to the physical size of the cosmic dust grains mixed in with the gas. These microscopic grains are exceptionally good at catching and scattering shorter wavelengths of light, which is blue light.
Okay, that makes sense.
The longer red wavelengths of light just pass right through the dust unobstructed. So when we look at the cloud, all we see is the scattered blue starlight bouncing back at us.
This sounds exactly like why the sky on Earth is blue during the day.
It is the exact same underlying physics, a process called Rayleigh scattering. In our atmosphere, it's nitrogen and oxygen molecules scattering the sun's blue light. In a reflection nebula, like the gorgeous blue haze surrounding the Pleiades star cluster, it's microscopic silicates and carbon dust scattering the light of the stars.
Okay, so we have emission nebulae glowing red from ionization and reflection nebulae glowing blue from scattered starlight. But obviously, if emission nebulae are blasting out light and reflection nebulae are scattering it, there has to be a scenario where the dust is just too thick for either. What happens when the light simply can't get through at all?
That creates the third and visually most menacing category, dark nebulae. These are regions where the concentration of cosmic dust is so dense, so cold, and so thick that it completely absorbs and blocks all visible light coming from any stars or glowing gas behind it.
It looks like someone took a hole punch to the universe. The classic example is the Horsehead Nebula. You have this vibrant red emission nebula in the background, and jutting up right in front of it is this pitch black silhouette that genuinely looks like a night piece from a chessboard.
It really does.
It just looks like a total void.
When we talk about this dust blocking the light, it's really important to clarify what dust means in the interstellar medium. This isn't the lint you sweep up off your floor. Cosmic dust is made of microscopic smoke-like particles, silicates, graphite, carbon compounds, and tiny nanodiamonds.
Nanodiamonds.
Yeah, and all of it is coated in layers of frozen ice.
So it's essentially a massive cloud of microscopic frozen soot.
Yes, and these dark frozen soot clouds are actually the most crucial structures in our entire story today. Because they are so thick, they act as cosmic shields. They block out the harsh, sterilizing radiation from the rest of the galaxy. Deep inside the pitch-black core of a dark nebula, the temperature drops down to roughly 10 to 20 Kelvin. For context, 0 Kelvin is absolute zero, where all molecular motion completely stops. Liquid nitrogen, which freezes things instantly on Earth, is around 77 Kelvin. So at 10 Kelvin, we are talking about an environment so unfathomably cold that it challenges our understanding of chemistry.
We used to assume that space was far too cold and barren for complex chemistry to occur. I mean, if molecules aren't moving, they can't bump into each other and react. But modern radio and infrared telescopes have completely rewritten that assumption by looking inside these dark nebulae.
Because even at 10 Kelvin, those tiny grains of silicate and nanodiamonds are acting like microscopic laboratory tables.
Exactly. Individual atoms of carbon, oxygen, nitrogen, and hydrogen drift through the cloud and physically freeze onto the surface of these dust grains. Once they are stuck on that icy surface, they are forced into close proximity. Over millions of years, they slowly bond together, they form water ice, they form ammonia, they form methanol, and it goes way beyond just simple water and ammonia, according to the data. Deep inside these freezing, isolated dark nebulae, we are finding the precursors to amino acids. We are finding the chemical building blocks for biological proteins.
It is a profound realization. The molecular foundations of life are not uniquely forged in warm, bubbling oceans on a rocky planet. The precursor chemistry required to build living tissue is actively being assembled on microscopic nanodiamonds in a freezing vacuum, hundreds of light years from nowhere.
Millions of years before a star or a planet even exists to host them.
Yes, exactly.
It's deeply humbling to realize that when you pour a glass of water, or you look at the carbon making up the cells in your own hand, well, that material didn't originate on Earth. The chemistry of your biology was processed in the freezing depths of a dark nebula. We are a biological extension of these cosmic clouds.
It's beautiful, really, but before we move to how those clouds collapse, we should quickly touch on the fourth visual category, just to complete the set, and that is the planetary nebula.
Which is completely frustrating, because it has absolutely nothing to do with planets.
We can blame William Herschel in the late 1700s for that one. When he looked at these specific objects through his early telescope, they looked like small, perfectly round, greenish-blue disks. They strongly resembled the planets Uranus or Neptune, so, lacking a better term, he called them planetary nebulae, and the name unfortunately stuck.
But if they aren't planets forming, what is actually happening?
They are the spectacular, lingering death shrouds of sun-like stars. When a medium-sized star reaches the very end of its life, it doesn't explode violently, it slowly destabilizes, and its outer layers of gas are popped outward into space, expanding in a massive glowing shell.
Oh, wow.
The dead, exposed core of the star, a white dwarf, sits in the absolute center, pumping out UV radiation that makes that expanding bubble of gas glow like a neon sign.
Like the Ring Nebula. It looked like a perfect glowing smoke ring floating in the void, with a tiny white dot in the center.
Yes. So our four categories represent a life cycle. Dark nebulae are the hidden incubators. Emission and reflection nebulae are the chaotic nurseries where young stars are actively bursting into the universe. And planetary nebulae are the beautiful, ghostly remnants of a star's death.
So, if we focus on those hidden incubators, the dark nebulae, we have these massive 10 Kelvin chemical-rich clouds of soot and gas. And they are physically stable. They can sit there for millions of years, perfectly balanced, but obviously they don't stay clouds forever. Something has to force them to become a burning star.
They are locked in a delicate tug of war. On one side, you have the inward pull of gravity. All those atoms of gas and dust have mass, so they naturally want to pull each other together. On the other side, you have outward thermal pressure.
Even at 10 Kelvin?
Yes, even at 10 Kelvin, the gas particles have a tiny amount of heat and kinetic energy, causing them to bump into each other and push outward. As long as the outward thermal push perfectly balances the inward gravitational pull, the cloud remains a stable nebula.
But the universe is a messy, violent place. Something eventually comes along to break that tie.
It requires a trigger. The most common and spectacular trigger is a shock wave from a nearby supernova. Imagine a massive star ending its life in a cataclysmic explosion. It sends a wall of energy and stellar material plowing through the interstellar medium at thousands of kilometers per second.
That's terrifying.
It is, and when that shock wave slams into our quiet, stable, dark nebula, it acts like a cosmic snowplow. It violently compresses the gas and dust on the leading edge.
And when you squeeze gas into a tighter space, you force the particles closer together, which means the gravitational attraction between those particles suddenly spikes.
And that breaks the tie. Gravity suddenly has the upper hand. If we connect this to the bigger picture, this transition is governed by a fundamental law of astrophysics called the Jeans criterion.
Named after Sir James Jeans, right?
Yes, the British physicist. It is the mathematical threshold where gravity finally overcomes outward gas pressure, dooming the cloud to collapse inward on itself.
And this perfectly explains why star formation requires the cloud to be so unbelievably cold. If the nebula was hot, the gas particles would be zipping around frantically, generating massive outward thermal pressure. Gravity wouldn't be strong enough to pull them together.
Precisely.
But because the dark nebula is hovering near absolute zero, the outward pressure is weak and lethargic. When the supernova shockwave hits, gravity easily wins the gene's criterion tug of war.
The cold is an absolute physical necessity for a star to be born.
So gravity wins, and the massive cloud begins to fall inward on itself. But because these giant molecular clouds are so vast and uneven, full of dense pockets and swirling eddies, they don't just shrink down into one single humongous star.
They shatter. The process is called fragmentation. As the overall cloud compresses, the naturally denser pockets inside the cloud reach their own localized genes criterion. They become gravitationally dominant in their own little neighborhoods and break away from the main collapse.
So a single massive dark nebula shatters into hundreds or even thousands of smaller individual collapsing clumps.
And each of those smaller clumps will go on to form its own individual star, or perhaps a small binary system. This fragmentation is the reason stars are almost never born in isolation. They're born in massive litters, forming dense star clusters like the Pleiades.
Let's track just one of those shattered clumps. We have a single core of gas, destined to become a star, falling inward under its own crushing gravity. As it gets smaller and tighter, it encounters a new physics problem: the conservation of angular momentum.
When you have a giant cloud of gas drifting through the galaxy, it is physically impossible for it to be perfectly stationary. It will always have some microscopic amount of rotation, just a lazy, almost imperceptible spin.
Right.
But the law of conservation of angular momentum states that as a spinning object decreases in size, its rotational speed must increase to conserve that total angular energy.
It's the classic ice skater physics from the sources. An ice skater goes into a spin with her arms stretched wide. She's spinning slowly. But the moment she pulls her arms in tight against her chest, her rotation suddenly violently accelerates.
The exact same thing happens to our collapsing gas cloud. As the material falls inward, getting smaller and smaller, that lazy drift amplifies into a violent, rapid spin. And this extreme rotation fundamentally alters the shape of the collapse.
How so?
Because the material is whipping around so fast, centrifugal force physically prevents a lot of the gas from falling straight down into the exact center.
Instead, the material along the equator gets flung outward. It flattens out into a pancake.
We call it a protoplanetary disk or an accretion disk. You end up with a dense spherical core in the absolute center, which will become the star, surrounded by a massive, flat, swirling disk of leftover gas and dust.
And that flattening is incredibly lucky for us. If the cloud didn't spin, if the gas just fell directly into the center, the star would consume 100% of the material. There would be absolutely nothing left over in orbit to build planets.
That's entirely correct.
The conservation of angular momentum is the physical reason the Earth has material to exist.
Without that rotational physics, the universe would be completely devoid of planetary systems. It would just be lonely, solitary stars.
So the disk is swirling, but in the center, that dense core is gathering more and more mass. It's compressing tighter and tighter. And this triggers another milestone: adiabatic heating, which, sounds like heavy jargon, but it's actually something you can feel in everyday life.
Oh, the bike pump example.
Yes. If you take a manual bicycle pump and vigorously pump up a tire, the metal cylinder of the pump gets physically hot in your hands. Squeezing a gas into a smaller volume generates heat.
That is adiabatic heating perfectly demonstrated. In the early stages of our cloud fragment collapsing, the gas is still relatively thin, so the heat generated by the compression simply radiates away into space as infrared light. The cloud remains cool.
But eventually,
the core becomes so tightly packed, so dense with material, that it becomes completely opaque.
the heat gets trapped. It can't radiate away anymore.
The infrared radiation is trapped inside the core, and the temperature violently skyrockets. It surges from 10 Kelvin to thousands of degrees. This massive spike in heat creates immense internal thermal pressure, which acts like a sudden brake. It halts the rapid free-fall collapse of the gas.
And when that free fall halts, The object officially enters its awkward teenage years. It is no longer just a collapsing nebula clump, it has become a protostar.
The protostar phase is one of the most dynamic yet hidden stages of stellar evolution.
Here's where it gets really interesting, because it's a profound paradox. The core is thousands of degrees hot. It is glowing intensely. It has massive amounts of energy. But there is absolutely zero nuclear fusion happening inside of it.
None at all.
It is a star powered entirely by gravity, not nuclear fire.
Yeah.
How does gravity generate enough energy to make a star glow?
It is entirely powered by kinetic impact. The protostar is still slowly, agonizingly contracting, and its gravity is aggressively pulling in material from the surrounding protoplanetary disk. As that gas falls from a great distance and violently smatters onto the surface of the protostar, its kinetic energy of motion is instantly converted into intense thermal energy.
It is literally glowing from the friction and impact of gravity crushing material onto its surface.
Yes. But to a standard telescope, the protostar is completely invisible. It is still buried deep inside that massive, opaque envelope of dust from the original nebula. Visible light simply cannot penetrate the soot.
Which presents a massive problem for astronomers. If the dust is completely opaque to visible light, standard telescopes are useless. They must have to use infrared to see the heat bleeding through the dust.
That is precisely why telescopes like Spitzer and now the James Webb Space Telescope are revolutionary. Infrared light operates at much longer wavelengths than visible light, allowing it to glide right through the microscopic dust particles without scattering.
Like X-ray vision.
Basically, yeah. When JWST looks at a dark nebula, the black dust disappears, and we see these brilliant, glowing protostars buried inside, like hot coals glowing underneath a pile of dark ash.
When we look at them in infrared, we see that they aren't just sitting there quietly absorbing material. They are throwing massive tantrums. They are launching these violent jets of material called bipolar outflows.
Remember that the protostar and its surrounding disk are spinning incredibly fast due to angular momentum. As more and more material falls onto the protostar, it spins faster and faster, to the point where the protostar is in real danger of spinning itself apart. It desperately needs an exhaust valve to shed some of that rotational energy.
So it uses its own magnetic field as an exhaust pipe.
The protostar develops intense, powerful magnetic fields. But because the star is spinning differentially, the equator spins faster than the poles, those magnetic field lines get dragged and twisted up like tightly wound rubber bands.
That sounds violently unstable.
Yeah, it is. Eventually, they become so coiled that they channel a huge percentage of the infalling gas away from the surface, accelerating it outward and blasting it away from the star's north and south poles.
And these jets are catastrophic. They shoot out into space, hundreds of kilometers per second, stretching for entire light years, violently slamming into the surrounding nebula and creating glowing shockwaves known as Herbig-Haro objects.
It is a spectacularly violent way for the star to break its own rotation. And during this chaotic period, the core is still slowly compressing, getting hotter and hotter, until it hits about 1 million degrees Kelvin. At that temperature, we see a temporary, short-lived spark of ignition, deuterium burning.
Deuterium is essentially heavy hydrogen, right?
Yeah.
A normal hydrogen atom is just one proton. Deuterium has a proton and a neutron.
Exactly.
And because of that extra neutron, it is physically easier to smash together. While normal hydrogen requires 10 million degrees to fuse, deuterium can ignite at just 1 million degrees.
So as the core temperature hits that 1 million degree mark, the deuterium suddenly ignites. Nuclear fusion briefly begins. The sudden burst of energy pushes outward, significantly slowing down the protostar's contraction. It acts like an emergency brake, stabilizing the young star.
But deuterium is incredibly rare. Only about 1 in every 100,000 hydrogen atoms in the universe has that extra neutron. So the protostar burns through this emergency fuel supply very quickly.
Very quickly, yes.
Once the deuterium is gone, gravity takes over again, the core continues to compress, and the temperature marches steadily toward the main event.
But before true ignition happens, the star enters its final, most erratic pre-main sequence phase, the T-Tauri phase.
Named after T Tauri, a notoriously unpredictable young star discovered in the constellation of Taurus. This phase can last anywhere from 10 to 100 million years for a star the size of our sun. What makes the T Tauri phase so chaotic?
The hallmark of a T-Tauri star is extreme magnetic instability. The inside of the star is fully convective, meaning the hot plasma is boiling and churning violently, constantly bringing material from the deep interior up to the surface.
Like a boiling pot of water.
Yeah, but plasma, this massive churning, heavily twists and distorts the star's magnetic fields, causing them to snap and reconnect, generating colossal solar flares and immensely powerful stellar winds.
We are talking about stellar winds that make the current solar wind from our sun look like a gentle breeze. These winds are ferocious, and they perform a critical, life-saving function for the solar system.
The T-Tauri winds essentially clear the table. Up until this point, the young star has been surrounded by the thick protoplanetary disk of gas and dust. But if that gas remained there indefinitely, the newly forming planets in the disk would just keep experiencing friction.
Oh, I see where this is going.
They would lose orbital momentum, spiral inward, and eventually plunge directly into the star.
The star would literally eat its own planets. But the T-Tauri winds act like a leaf blower. They physically blast all the remaining hydrogen and helium gas out of the planetary system, leaving behind only the heavier dust grains, rocks, and baby planets.
That's what saves them. It stops the accretion process, locks in the final mass of the planets, and reveals the young solar system to the universe for the first time.
It is a phenomenal process to witness. The ALMA radio telescope array actually captured an image of a young star called HL Tauri in exactly this phase.
Oh, the HL Tauri image is legendary.
I look at that image from the sources, and it is staggering. You can see the flat disk of dust surrounding the star, but it's not smooth. There are clear, dark, concentric gaps carved into the disk. It looks like the grooves on a vinyl record.
It really does.
And those dark gaps are exactly where baby planets are currently orbiting, sweeping up the dust like snow plows.
When you look at the HL Tauri image, you are looking into a cosmic mirror. You are witnessing a direct snapshot of what our own solar system looked like 4.6 billion years ago, right at the moment the Earth was just starting to sweep up its orbit.
Okay, so the ferocious T-Tauri winds have blown away the cosmic smoke. The planetary disk is settling down into distinct orbits. But deep inside the core of the star, the gravity is still crushing relentlessly. The temperature is climbing higher and higher, 6 million degrees, 8 million. And then finally, the core reaches the magic threshold, 10 million Kelvin.
10 million Kelvin is the absolute tipping point. At this temperature, the hydrogen protons in the core are moving with such extreme kinetic velocity that they can overcome their natural electrostatic repulsion.
Because protons are positively charged, they naturally want to violently repel each other, like pushing the north poles of two magnets together.
Exactly. But at 10 million degrees, coupled with quantum tunneling effects, they're moving so incredibly fast that they smash together before they have a chance to repel. They physically fuse. True nuclear fusion has officially begun. We have ignition, the moment a star is officially born.
And the engine powering that ignition is an elegant yet violently powerful mechanism called the proton-proton chain. How does the star actually turn hydrogen into light?
It is a precise multi-step process. In the chaotic core, two hydrogen protons smash together. One proton instantly decays into a neutron, releasing a positron and a neutrino, creating a nucleus of deuterium.
Okay, step one.
Then, that deuterium nucleus slams into another free proton, creating a lightweight version of helium called helium-3, and releasing a massive burst of gamma-ray radiation. Finally, two of these helium-3 nuclei collide with massive force, producing one incredibly stable, heavy nucleus of normal helium-4, while kicking two leftover protons back into the core to start the cycle all over again.
So the net result of this entire chaotic dance is taking four individual hydrogen atoms, crushing them together, and forging one single helium atom.
But here is the critical, universe-defining twist. If you put that one new helium atom on a scale, its mass is very slightly less than the combined mass of the four original hydrogen atoms. Roughly 0.7% of the physical matter simply disappears during the fusion process.
And we know from Einstein that matter cannot be destroyed. E equals mc squared. Energy equals mass times the speed of light squared.
Mass is converted directly into pure radiating energy. And because the c in that equation, the speed of light, is an astronomically huge number, even a microscopic fraction of missing mass translates into an apocalyptic release of energy.
This gamma-ray energy radiates outward from the core with unimaginable force. And finally, after millions of years of gravity winning the tug of war, that outward radiation pressure perfectly pushes back. It completely counteracts the inward crushing weight of the star's own gravity.
The tug of war is permanently tied. Physicists call this state hydrostatic equilibrium. The star stops contracting, it stabilizes. It officially joins the main sequence of its life.
To give you a visceral sense of how powerful this proton chain engine is, let's look at the closest star we have, our sun. Every single second, 1 2, 3 every second, the core of our sun crushes 600 million tons of hydrogen into helium.
It is a scale of consumption that defies human logic.
Out of that 600 million tons fusing every second, about 4 million tons of physical matter completely vanishes from existence, transformed instantly into pure radiating energy. The sunlight hitting your face right now is a result of 4 million tons of matter annihilating itself in the sun's core 8 minutes ago.
And that raises an obvious paradox. If the sun is actively destroying 600 million tons of its own fuel every single second, how is it possible that it's been burning for 4.6 billion years and still has enough fuel left to burn for another 5 billion years? Why doesn't it run out of gas in a few weeks?
It has to come down to the sheer, incomprehensible volume of the sun. It is so massive that 600 million tons a second is literally a rounding error.
Precisely. The sun contains roughly 2 nonillion kilograms of mass. That is a 2 followed by 30 zeros. It is so astronomically huge that over its entire 10 billion year lifespan, it will only fuse about 10% of the total hydrogen available in its core. It is the ultimate exercise in cosmic efficiency.
And the proton chain is just the slow, steady engine for medium and small stars. If a star is significantly larger, above roughly 1.3 times the mass of our sun, it abandons the proton chain entirely. The core gravity is so intense and the temperatures are so extreme that it switches to a much faster, more aggressive engine called the CNO cycle.
The CNO cycle stands for carbon-nitrogen-oxygen cycle. In these massive stars, core temperatures routinely exceed 15 million Kelvin. At those blistering temperatures, the star uses trace amounts of carbon, nitrogen, and oxygen already present in the core to fundamentally accelerate the fusion of hydrogen into helium.
So it's not actually burning the carbon away. The carbon is just acting as a chemical catalyst, facilitating the reaction so it happens thousands of times faster.
Exactly. The carbon grabs a proton, turns into nitrogen, grabs another, turns into oxygen, decays, and eventually spits out a helium nucleus and turns right back into carbon, ready to go again. Because this catalytic process is so incredibly efficient at high temperatures, these massive stars produce energy at a staggering, almost reckless rate. They shine thousands or even millions of times brighter than our sun.
But they pay the ultimate price for that brilliance. Which brings us to a fundamental rule of astrophysics. Mass is destiny. A star's entire life story, how bright it shines, how long it lives, and exactly how violently it dies, is dictated purely by how much gas it managed to gather during that initial nebula collapse.
It seems highly counterintuitive. You would naturally assume that a massive star loaded with vastly more hydrogen fuel would live much longer than a small star.
Like a larger gas tank in a car.
Right. But because that massive gravity crushes the core so intensely, driving the temperature up and engaging that aggressive CNO cycle, massive stars burn through their fuel at terrifying speeds. While our modest sun will live for 10 billion years, a massive O-type star might exhaust its entire core in just 5 to 10 million years. They live furiously fast, and they die incredibly young.
Let's run through the full spectrum of that destiny. Let's look at the hierarchy of star formation, starting at the very bottom. The cosmic failures, brown dwarfs.
If a collapsing clump of gas from a nebula fails to gather at least 80 Jupiter masses worth of material, which is roughly 0.08 times the mass of our sun, its core will never generate enough gravitational pressure to reach that critical 10 million Kelvin threshold. It will trigger that brief deuterium spark, glow dimly with the leftover friction heat of its collapse, and then just slowly, quietly cool off into a dark, frozen sphere. It is a failed star.
Just a little too small to ignite the main engine. But right above the brown dwarfs, you have the absolute rulers of the universe, red dwarfs or M-type stars.
Red dwarfs make up an astonishing 75% of all the stars in the Milky Way galaxy. They are just barely massive enough to sustain true hydrogen fusion. But because their internal gravity is relatively weak, the fusion process operates at an incredibly slow, gentle crawl.
They are sipping their fuel through a microscopic straw while the massive stars are chugging it from a fire hose.
And red dwarfs have another distinct advantage. While our sun only fuses the hydrogen located strictly in its innermost core, red dwarfs are entirely convective. Their interior boils and churns continuously from the core all the way to the surface. This churning constantly drags fresh, unburned hydrogen from the outer layers directly down into the fusion engine. They can metabolize almost 100% of their entire mass.
Meaning their lifespans are effectively infinite on a human scale. A red dwarf can burn steadily for trillions of years. And since the universe itself is only 13.8 billion years old, that means not a single red dwarf in the history of the cosmos has ever died of old age yet. Every red dwarf ever born is still shining.
They will be the last beacons of light remaining long after every other star in the universe has burned out.
Then, in the middle of the pack, you have medium stars like our sun living a comfortable 10 billion year life. And at the absolute top, you have the rock stars, the O-type and B-type blue giants, the ones lighting up the emission nebulae, burning hot, dying young, and ultimately detonating in cataclysmic supernova explosions. But there is one more detail about star formation that completely challenges how we view our place in the galaxy.
Oh, the binary systems.
Yes. When we look up at our solitary sun, we assume that being alone is normal. But the data shows that over half of all sun-like stars are actually part of binary systems. 2 stars, orbiting each other.
Sometimes even trinary systems with 3 stars locked in a complex gravitational dance.
Why is forming a binary system the default setting for the universe, rather than a single star?
This raises an important question, and it goes back to the fragmentation of the nebula. When the giant molecular cloud shatters into smaller cores, those clumps are often very close to one another, sharing the same localized pocket of gravity. As they collapse and spin, it is extremely common for the angular momentum to cause the Clyde fragment to split into 2 separate cores that stabilize in a shared, tight orbit around a common center of mass.
So they're born as twins from the exact same disk of gas. Which immediately makes you wonder, if over 50% of stars form as twins, why is our sun completely alone? Are we the cosmic weirdos?
We are definitely in the minority, and it is a fascinating area of active astrophysical research. Some models strongly suggest that our sun likely did form with a binary companion inside our original stellar nursery cluster.
Wait, really?
Yeah, but because star clusters are chaotic, crowded environments, gravitational interactions with other passing stars can easily disrupt delicate orbits. It is highly probable that our sun's twin was gravitationally stripped away and flung out into the galaxy billions of years ago.
I absolutely love the idea of a lost sibling sun, forged from the exact same dark nebula, wandering somewhere on the other side of the Milky Way, completely unaware of its connection to Earth.
It's a great thought experiment.
So we have extensively mapped out the physics. We understand the illusion of the dark clouds, the critical genes criterion collapse, the spin of the protoplanetary disks, the hidden teenage protostars, and the violent ignition of the proton chain. But what does all of this actually look like when we step outside and look up at the night sky? Let's take a tour of the most famous stellar neighborhoods in our galaxy to see these physics in action. Let's start with one you could literally walk outside and see tonight with your bare eyes, the Orion Nebula.
The Orion Nebula, officially cataloged as Messier 42, is arguably the most famous and intensely studied star-forming region in existence because of its immense brightness and proximity. If you go outside in the winter and look at the constellation of Orion the Hunter, just below his distinctive 3-star belt is a fainter vertical line of stars that makes up his sword. If you look closely at the middle star in that sword, it looks a little fuzzy. That isn't a star at all, that is the Orion Nebula.
And cosmically speaking, it is practically in our backyard.
It is only about 1,300 light years away. Because it is so close, it serves as humanity's primary laboratory for studying the exact stellar physics we've been discussing. It is a classic emission nebula spanning about 24 light years across. The reason it glows so violently in red and green is due to a very tight cluster of massive, blistering young O-type stars right in its absolute center, known as the trapezium cluster. Their UV radiation is ionizing the entire cavern of gas.
But what's truly wild about Orion is that it isn't a static painting. It is an active churning factory. If you were to hop in a time machine and look at the sword of Orion 100,000 years from now, it would look completely different.
Because right now, hidden deep inside the dark, opaque dust lanes behind the glowing gas, infrared telescopes have detected dozens, if not hundreds, of protostars actively gathering mass. In roughly 100,000 years, the violent T-Tauri winds from those newly ignited stars will finally blow the dust away. A whole new, brilliant cluster of stars will suddenly burst into view, permanently altering the shape of the constellation.
Moving further out and scaling up significantly, we have the Carina Nebula.
Situated about 7,500 light years away, the Carina Nebula is a true monster. It is one of the largest and most volatile star-forming regions in our entire galaxy, spanning over 300 light years across.
And it is famous for housing one of the most terrifying objects in the Milky Way, Eta Carinae. This star is essentially a ticking time bomb.
Eta Carinae is an absolute behemoth, an unstable hypergent likely over 100 times the mass of our sun. Because of its extreme mass, its core is burning fuel at a ferocious, unsustainable rate, constantly teetering on the edge of blowing itself apart. It routinely produces massive eruptions, ejecting entire solar masses of gas into space. It is fully expected to detonate in a hypernova explosion in the near astronomical future. The intense, violent radiation from Eta Carinae and dozens of surrounding O-type stars is aggressively carving and shaping the entire structure of the Carina Nebula.
And the Carina Nebula is where the James Webb Space Telescope took that iconic cosmic cliffs image in 2022. That image was a watershed moment because it perfectly demonstrated the power of infrared astronomy. When you look at the edge of the Carina Nebula in visible light, it just looks like a solid, impenetrable mountain range of brown dust. But when JWST turned its infrared sensors on it, it peered right through the dust and unveiled dozens of those hidden protostars we discussed. You could clearly see the bipolar Herbig-Haro jets violently blasting out of the cloud into space. We were literally watching stars being born in real time.
Next on the tour is a nebula so unimaginably huge it defies logical comprehension. The Tarantula Nebula.
And this one isn't even in the Milky Way.
No, the Tarantula Nebula, or 30 Doradus, is located in the Large Magellanic Cloud, which is a small satellite galaxy actively orbiting the Milky Way about 160,000 light-years away.
The scale of this structure is breathtaking. It spans 1,000 light-years across.
It is the single largest, most furiously active star-forming region in our entire local group of galaxies. It contains a central cluster of stars, so massive and dense that it includes individual stars calculated to be up to 300 times the mass of our Sun. The radiation environment inside the Tarantula Nebula is so extreme, so intensely violent, that astrophysicists study it because it perfectly mimics the harsh conditions of the very early universe right after the Big Bang.
To really grasp the sheer size of the Tarantula Nebula, consider this: if you somehow magically transported the Tarantula Nebula from its current location and dropped it exactly where the Orion Nebula is, just 1,300 light-years away, it would be so unimaginably massive and so blisteringly bright that it would span a huge chunk of our night sky. It would glow significantly brighter than the full moon, and the glowing gas would literally cast distinct shadows on Earth at midnight.
It perfectly illustrates the sheer scale giant molecular clouds can achieve at their absolute maximum.
Bringing it back closer to home, we have the Lagoon Nebula, about 4,000 light-years away, and this region contains a phenomenon that sounds like science fiction: giant interstellar tornadoes.
Yes, deep within the Lagoon Nebula, Hubble captured images of massive, twisting, funnel-like structures of gas. These are complex Herbig-Haro objects. When the high-speed supersonic jets of gas blasting from the poles of young protostars slam into the thick surrounding nebula, the collision creates immense shear forces. It twists and winds the gas into swirling vortexes. These interstellar tornadoes are half a light-year long.
We are talking about a funnel cloud of gas and dust, many times larger than our entire solar system, just violently tearing through the interstellar medium. Which brings us to perhaps the most iconic, recognizable space image of the last 50 years. The Eagle Nebula, and specifically the structure within it known as the Pillars of Creation.
The Pillars of Creation are an absolute masterpiece of cosmic architecture. They consist of 3 towering, majestic columns of dense, cold gas and dust, roughly 1 to 4 light-years tall. They jut out into a massive, empty void that has been carved away by the intense ultraviolet radiation of a nearby cluster of massive young stars.
And that intense UV radiation is actively destroying the pillars, right? It's a process called photoevaporation. The radiation acts like a blowtorch, slowly boiling and sandblasting away the outer layers of the gas columns, slowly revealing the dense, dark protostellar cores hiding inside the very tips of the pillars.
It is a textbook example of triggered star formation. The external pressure from the radiation is violently squeezing the gas inside the pillars, forcing it to reach the Jeans criterion and collapse into stars much faster than it normally would if left alone.
So what does this all mean? When we look at that beautiful, serene poster on our wall of the Pillars of Creation, we are looking at a cosmic ghost. Because physics, specifically the speed of light, dictates a dark secret about those pillars.
This is where astrophysics intersects with the philosophical reality of a vast universe constrained by the finite speed of light. The Eagle Nebula is located about 7,000 light-years away from Earth. That means the photons of light hitting the lens of the Hubble telescope or hitting your eye literally left those pillars 7,000 years ago. When you look at that famous photo, you are not seeing the pillars as they are today. You are looking at a snapshot of the deep past.
And a lot can happen to a delicate structure of gas in 7,000 years.
Indeed. In recent years, infrared telescopes like Spitzer peered into the region around the pillars and discovered the unmistakable glowing signature of an expanding supernova shockwave. Based on the speed and trajectory of that superheated gas, astrophysicists calculated that this shockwave violently slammed into the pillars of creation and completely obliterated them roughly 6,000 years ago.
Wait, so the pillars don't exist anymore. They were wiped out 6,000 years ago by the explosive death of a massive nearby star.
They have been completely blown apart. But because of the immense 7,000-year speed of light delay, the visual evidence of that destruction, the light from the blast, and the shattering of the columns is still traveling across the void toward us. It won't arrive here on Earth for another 1,000 years. For the next millennium, humanity will continue to look up at the sky and admire a perfectly peaceful, majestic image of a structure that has already been violently destroyed. It is an active crime scene, and the evidence simply hasn't arrived yet.
It forces you to completely rethink what the word now actually means. We are literally peering into a time machine every time we look at a nebula, and that destructive supernova shockwave brings us perfectly to the final and perhaps most profound section of our deep dive, the grand recycling program of the universe. Because that supernova that wiped out the pillars of creation, it is not just a destroyer, it is the exact same mechanism that physically created the Earth and physically created every single person listening to this right now.
This is the ultimate scientific and philosophical takeaway from studying star formation. Nebulae are not just isolated factories cranking out stars. They are critical nodes in a continuous, billions of years old cycle of stellar recycling.
The cycle is beautiful in its simplicity. A cold nebula collapses to become a star. The star lives its life. The star dies either by gently puffing out a planetary nebula or violently detonating in a supernova. And that death physically enriches the surrounding space with brand new, heavier elements, which eventually cool down and collapse back into a new, enriched nebula.
To understand why this matters, you have to look at the very beginning. Right after the Big Bang, the universe was chemically sterile. It consisted almost entirely of just two elements, hydrogen and helium, with a tiny dash of lithium. That was it. No carbon, no oxygen, no iron, no calcium, no silicon.
Which means the very first stars born in the universe, what astronomers call population 3 stars, were made purely of hydrogen and helium. And because there were no heavy elements like silicon or iron to build rocks, those first stars couldn't possibly have had rocky planets like Earth orbiting them.
Precisely. Planetary systems and biological life were physically impossible in the early universe. The ingredients didn't exist. But inside the blazing high-pressure cores of those massive population through stars, nuclear fusion was acting like a cosmic alchemist. After they burned through their hydrogen, they started fusing helium into carbon, then carbon into oxygen, then oxygen into neon, silicon, all the way up to iron. And when those massive first-generation stars finally died in catastrophic supernovae, they blasted all those freshly forged heavy elements out into the void.
They polluted the pristine interstellar medium with the good stuff, the heavy metals.
Yes, and that newly enriched material drifted through space, mixed with massive clouds of unburned hydrogen, cooled down over millions of years, and became a second generation of dark nebulae. Then, a new shockwave triggers a collapse, and a new generation of stars is born. But this time, the gas and the swirling protoplanetary disks contain those heavy trace elements.
Which brings us directly to our sun. The chemistry of our solar system proves that our sun is a second, or possibly even third generation star.
The very existence of the Earth, a dense ball of rock and iron, proves that the dark nebula that birthed our solar system 4.6 billion years ago was highly enriched by the explosive deaths of previous stars. We are built from the wreckage of dead suns.
And we actually have physical, tangible proof of the specific trigger that created us. When scientists analyze ancient meteorites, which are basically pristine, leftover rubble from the exact moment our solar system formed, they find something incredible. They find the decay products of specific, short-lived radioactive isotopes, like aluminum-26.
That is the smoking gun. Aluminum-26 is an isotope that can only be forged in the extreme, chaotic violence of a supernova explosion, and it decays very quickly. The fact that it was present in the rocks forming our early solar system means a supernova had to have happened right next door, exactly at the moment our local cloud began to collapse.
The evidence strongly points to a narrative where 4.6 billion years ago, a massive ancient O-type star went supernova right near our local dark nebula. That specific shockwave violently injected those radioactive isotopes into our freezing cloud, and the sheer force of the blast caused the gene's criterion to tip, gravity 1. The cloud collapsed, the angular momentum flattened it into a spinning disk, adiabatic heating ignited the T-Tauri phase, and eventually the proton chain ignited our sun, leaving behind a swirling disk of enriched stardust that eventually clumped together to become Earth.
Without that specific dying star exploding, our local cloud might still just be a freezing, dark, empty void today. The violent death of massive stars is a strict, non-negotiable physical requirement for life in the cosmos. Without supernovae, the universe would be chemically impoverished. It would remain a sterile ocean of hydrogen gas forever.
Let's bring this all the way home, because when we say you are made of stardust, it's become a bit of a poetic cliche. People put it on inspirational posters and bumper stickers, but based on everything we've broken down today, it is not poetry. It is a hardcore, literal, scientific reality. Think about the iron in your blood that is carrying oxygen to your brain right now. Think about the calcium making up the bones in your legs. Think about the carbon that forms the structural backbone of every single cell in your body. Where did it physically come from?
Every single atom of those heavy elements was forged inside the pressurized nuclear furnace of an ancient, massive star that lived a short, violent life and exploded billions of years before the Earth even existed. Those atoms were blasted into space, drifted through the freezing vacuum of a dark nebula, bonded onto a microscopic grain of silicate dust at 10 Kelvin, or swept up in a collapsing protoplanetary disk, baked in the intense radiation of our young T-Tauri sun, clumped together to form a molten planet, and eventually, through billions of years of geology and biology, found their way into you.
The atoms making up your body right now are ancient stellar shrapnel. You are quite literally the universe possessing consciousness and experiencing itself.
It is the most beautiful connection in all of science. The study of nebulae isn't just distant astronomy, it is genealogy. It is humanity looking through a telescope to find our deepest, oldest roots.
We have covered an incredible amount of ground today. From the visual illusion of empty space clouds to the violent gravitational tug-of-war of the genes criterion. We unmasked the hidden, temperamental teenage T-Tauri phase, the raw nuclear ignition of the proton chain converting millions of tons of matter into energy every second, and finally, the grand, billions of years long recycling program that directly connects the violent explosion of a massive star to the iron flowing in our veins. It completely shifts how you look up at the night sky. Those dark patches between the stars aren't empty space. They're pregnant, chemical-rich clouds, just waiting for a spark. And I want to leave you with one final mind-expanding thought to chew on as you go about the rest of your day. We talked extensively about the pillars of creation and how the vast speed of light creates a massive cosmic time delay. We're always looking deep into the past. We also learned that the specific trigger for star birth and planetary formation is the expanding shockwave of a dying star. Because the universe is so unimaginably vast and operates on this massive time delay, it is a statistical certainty that right now, at this exact second, a shockwave from a cataclysmic supernova is silently washing over an invisible, freezing, dark molecular cloud somewhere out there in the Milky Way. It is quietly compressing that gas. It is aggressively seeding that cloud with freshly forged heavy metals. It is setting the precise biological and chemical parameters for a brand new protoplanetary disk, and perhaps laying the foundations for a brand new form of life. A planetary system that won't even see its first sunrise for another 100 million years. You are the product of an ancient shockwave, and the universe is already preparing the next one.